Obviously, it's tempting to think of technologies that can directly suck out carbon dioxide from the atmosphere. That would make a life much easier as a game changer. For example, if you're driving around, flying around, shipping things, these are distributed sources. It's not like power plants, which are point sources and easier to install carbon capture apparatus and so on. But if you have a way of directly capturing from the air, these are also called direct air capture or DAC, then it would be amazing. Okay, so the methodologies that are already being tried, we'll look at some of them. They will end up being things like chemical scrubbers, where some chemical is used to take CO2 out of the air that's flowing through, like in the artificial tree. So the basic process is kind of well known, reproducible in the lab accurately and precisely. CO2 dissolves easily in water and produces carbonic acid, which is a weak acid. So easily gives up H+. That's what drives the weathering. So every time it rains, CO2 in the atmosphere can dissolve into water, produce carbonic acid, and create weathering. Depends on temperature as well. So that's a very, very slow process. Like that's very important at geologic time scales of millions of years, but on human life time, it's not very significant. But we'll talk about ways they could potentially be accelerated in terms of accelerated weathering, right? But in terms of direct air capture, you use chemicals like NaOH. I think this is sodium hydroxide, which obviously is it's something that's there in common cleaners we use in the bathroom and so on, which is a basic base. It is a base, so H plus from the carbonic acid can interact with react with a base to produce HCO3 minus, the bicarbonate, which is stable, and if it goes into the ocean, then it's used by species in the water like calcifying organisms, corals, diatoms, phytoplankton, other types of phytoplankton like coccolithophorids, and so on. Then carbon gets sequestered away, right? So HCO3 is much more stable. CO2 is also stable and very inert, not very good fuel, etc. So we are dealing with multiple things. Can CO2 be converted to energy? Can it be taken away and hidden somewhere, or can it be pulled out with these kind of reactions? Okay, so H2CO3, the carbonic acid, can go with sodium hydroxide to produce H plus bicarbonate plus sodium ion, which is basically part of the salt, right? Sodium and chlorine is a gas, sodium is a metal, together they make salt. Who knew? And you have the hydroxide. So you get water, sodium, and bicarbonate. So this is a good reaction if it can be driven successfully. So here is Climeworks Direct Air Capture or DAC facility near Zurich, Switzerland, which uses 18 modular, so you can see these 6 in each row, modular capture units to remove CO2 from the air. So air is just flowing through, and CO2 is being precipitated out. It's being mineralized. Amazing, right? So then CO2 is captured, purified, and used to enhance growth of vegetables in greenhouses, which are here in the background. CO2 fertilization is done. Remember, the vegetation basically opens stomata. It has moved nutrients and water with capillary action from the roots to the leaves, and stomata opens to capture CO2 without losing the valuable water. So stomatal conductivity depends on CO2 concentration, but if you enrich the atmosphere with CO2, then they can easily capture CO2 and do photosynthesis, right? That would work well in a greenhouse. Doing it in an open area is obviously not recommended because you'll be releasing CO2 into the atmosphere. Okay, so this is not really negative emissions yet, but a demonstration of the costs and issues associated with separating CO2 from the air is being done at some scale. Okay, the facility catches about 1,000 tons of CO2 per year, which is minuscule compared to the 20 gigatons we are aiming for. But every little technology innovation happens sometimes with small steps, like transistor, and then boom, you get all the way to semiconductors, right? Okay. This is a map showing from this EPA site talking about initial assessments of theoretical CO2 storage capacity, revealing an important and encouraging result. There is more than enough theoretical CO2 storage capacity in the world. Whether they are viable or not, they are theoretically sites for capturing, storing the CO2 that's captured. So this is easy, this is large enough to meet the likely storage needs at least for a century, and in many key regions the storage capacity is in the right places to meet current and future demands in terms of transportation, emission locations, etc. So you can see the numbers range from 1,300 in Canada to 3,900 gigatons CO2 here. Lower here because already the forests are functioning at some capacity. So these are additional storage sites. Okay, remember that. 260, 430, and so on and so forth. Okay, so North America here on this side has massive storage capacity. Okay. These are places where carbon capture and sequestration activities are already underway. Obviously, a lot again over US and Canada, but also over Mexico, somehow in Algeria, Saudi Arabia. Obviously, they have money to try these sorts of things. Australia, and up here. These Scandinavian countries are generally very progressive on renewables, carbon capture, and other green technologies, etc. Okay, so let's look at accelerated weathering as also a direct air capture. So this is Lawrence Livermore National Lab up in California, where scientists are examining ultramafic, I don't know how it's pronounced, rocks in Washington state. These rocks are rapidly reacting with CO2 and breaking down calcium and bicarbonate ions, leaving clays and unreacted blocks of rock behind. Okay, this is a site of a landslide, and rocks break down, more surface area is exposed, but they also create loose structure and can have landslides if there are extreme rain events and so on. But these igneous rocks actually have high content of chemicals that are easily weathered, like calcium carbonate, which is easily dissolved into carbonic acid, and when it flows into the ocean, Ca, calcium, is used by corals and diatoms and phytoplankton that form calcium carbonate shells, and if they dissolve, then that CO2 is released back. But if it sinks to the ocean bottom, then obviously carbon is sequestered away. In fact, many of the foraminifera and other phytoplankton that form calcium carbonate and fall to the bottom give us long past climate records, because their abundance and some crystal structures in them, like aragonite and calcite, tell us about temperatures and other properties from the past. So they are paleothermometers. So amazing, right, how life cycle works. And these are the sites of ultramafic rocks with basalts and anorthite, and shown also are the areas for potential in situ carbonation. So accelerated weathering possibilities. Okay, so we have to explore everything under the sun if it is net negative without creating other problems.